In other words, there's no net oxidation reduction going on in the sugars either, right? Which kind of makes sense if there's no net oxidation reduction going on between NAD and NADH. So these are the sort of chemical characteristics of what we call a fermentation. So it does have a sort of a specific biochemical meaning, right? Normally we use fermentation colloquially to mean, brewing beer, but in biochemical talk, it refers to this sort of reaction, right? You might recall as well that if you're exercising heavily and your lungs cannot get enough oxygen to your muscle tissue, so that you cannot deliver electrons from NADH to oxygen to form water, that NADH will instead start delivering electrons here, and the lactic acid that builds up will cause the strain in your muscle, the pain in the muscle when you're exercising too much. Okay. So the reaction is between pyruvate and lactate. We saw this actually as an example of a redox reaction, so we already looked at the delta E for it. You can look at the delta E from the table, right, from chapter 13. And this just illustrates sort of the overall cycle. Okay. So why don't we look at the mechanism is, and just so that we can see, I'm not going to draw everything out, but I'll just draw a little bit of NADH going to NAD, so that we can understand why NAD goes to NADH plus H plus, right? Because it's obscure unless you see it, how it works in the mechanism. So this is, I'm just drawing the nicotinamide part of the ring here. Remember that the nicotinamide ring has this funky amide side group there. And so in the redox reaction, NADH now, and so here's the R group. So the rest of NAD, all that, the adenine part of it is down there somewhere, off binding the enzyme and doing something down there, but not the chemistry, not the reaction. So here, electron density coming into this carbon, we have this hydride transfer. So this reaction here is the hydride transfer. So the hydride. Okay, and it goes to a histidine on lactate dehydrogenase. So there's different mechanisms here. It doesn't have to be a histidine on an enzyme, it could be something else, right? But whatever it is, there's going to be ways to move the hydrogen out of NADH. And so this is His 195, doesn't matter what the number is, and this is on the LDH enzyme. What did I do there? Totally messed that up. I forgot to draw pyruvate. Other than that, it was great. Don't feel badly when you're drawing something on the exam and something like that happens. Okay, so the hydride is going to pyruvate. This is pyruvate, right? And now here's the histidine on LDH. Okay. So this is pyruvate. So this is going to form lactate. And it's also going to form an imidazole with no proton on it. But this guy, right, so this is going to go to NAD. This is NADH. So now we've got, this is not carrying a positive charge, so there's NAD plus. And a single hydrogen here now. Okay. So this picks up a proton from solution to regenerate that form of the enzyme. So when this picks up a proton from solution, it's really NADH at upper left plus H plus on one side and NAD plus on the other. So that's why we always write NAD goes NADH plus H plus. Because there's going to be a proton that has to be picked up in order to reconstitute the active form of the enzyme in this case. I don't think this mechanism is in the book, and it's not one that you're going to have to write out, but I might show it to you and ask a question or something like that. Yeah.
So it sounds like this costs energy because you go from the ADH to the.
I mean, the cofactor, if you're going from NADH to NAD, the cofactor form we think of as low energy because it doesn't carry sort of energy-rich electrons that can go down an electron transport chain.
Yes.
Yeah,
And on top of that, the lactate has ill effects to the cells. So I'm trying to figure out why.
Well, it doesn't have ill effects to, for example, an E. coli cell that's growing anaerobically. And that's just its natural state, is to never have any oxygen. Right? I mean, you could argue that it has negative effects on your muscle because you couldn't get enough oxygen to your muscle.
I'm trying to figure out why this mechanism would even happen.
Why would it even happen?
Yeah. Is there like a reason we don't want pyruvate hanging around the?
Well, it's not that we don't, it's not so much that we don't want pyruvate, probably, but it's more that we need NAD. The reason this is happening is so we can get this, so that we can run more glycolysis. And if you have no oxygen, we have to have something else to regenerate NAD. I mean, it doesn't have to be direct. Maybe there's some abbreviated other pathway with a couple of other electron transfers in it, something like that. I mean, life is very varied, you know. But this is pretty common, and I'll show you in yeast it's a little different. Yeah.
And if I remember correctly, it also helps stimulate blood to go to those areas, and so that would be a physiological reason for this process to happen, to help get oxygen there.
Okay. Some kind of feedback. Yeah, I don't know about that. That's interesting. Yeah. Other questions? So, as I just mentioned, the other fermentation pathway is to go, is to take pyruvate, and rather than doing the redox reaction right on pyruvate, there's first a decarboxylation of pyruvate to form a 2-carbon compound. So this is a decarboxylation. TPP is thiamine pyrophosphate, okay, which is an important cofactor. I've got mechanisms for it on the next few slides, but I'm going to not go into them now, because after the first midterm, next week we'll be getting into an enzyme called pyruvate dehydrogenase complex that also uses thiamine pyrophosphate, so we can look at it there. But for now, just know that there's this cofactor called thiamine pyrophosphate that's involved in 1-carbon transfers, generally in metabolism. It's involved in decarboxylations as a kind of 1-carbon transfer, particularly. So pyruvate goes to acetaldehyde, and then the redox reaction on acetaldehyde goes to ethanol. Okay. In alcohol dehydrogenase, which is the enzyme here, rather than histidine, the electrons on acetaldehyde go on an oxygen and get stabilized by the zinc ion in the active site. So we can have different mechanisms here. But we've got pyruvate in this case.